Hello, welcome to the 11th lecture in the series of the lectures on tribology for the beginners. This lecture is on lubrication regime. Lubrication regime is a very important topic in tribology because it tells you what are the lubrication mode or a particular set of operating condition between two rubbing bodies. So this gives a fairly good understanding of the lubrication between the two bodies, and we can take appropriate measure depending on the operating conditions. So the first we go to to this picture. This picture tells us a marine propeller and the weather propeller shaft is borne by journal bearings. In fact, in many of the applications these days, ball or roller bearings are sufficient. But there are very few places where hydrodynamic journal bearings are still used for various reasons, and marine propeller shaft is one of them. This is a convenient way to explain the lubrication regime in terms of the working principles of hydrodynamic journal bearings. The picture tells us a fairly long propeller shaft where the propeller is shown on the left-hand side and the thrust produced by the propeller is transmitted to the hull by a thrust block, which is not shown here. But the main important thing in this case is that the propeller shaft is carried by a number of fairly large hydrodynamic journal bearings. Hydrodynamic journal bearings. And you can see that on the left-hand side, a journal bearing is a copper or bronze or babic metal bush, which is pushed inside a plumber block shown on the left-hand side. And in many cases, this is a typical way of carrying load while a shaft is rotating. So this tells us how the thrust produced in the propeller is transmitted to the hull using large hydrodynamic journal bearings. Now in hydrodynamic journal bearings, the shaft, as shown in the picture, rotates eccentrically within the bearing, and the lubricant film shown in a very accelerated form takes a shape like this, and the shaft rotates eccentrically. In fact, it is essential that the shaft rotates eccentrically. Otherwise, the wedge, which film wedge, which is responsible for reducing the hydrodynamic pressure generated. And here, the important parameters that is needed for the general bearings operation are viscosity, coefficient of viscosity eta, n is the speed, p is the load per unit area, small r is the radius of the general bearing, c is the clearance, radial clearance, and L is the length of the bearing. Now, it has been shown earlier, or it can be shown that the coefficient of friction is a function of three non-dimensional parameters, such as eta n by p, r by c, L by c. Now, eta n by p is often termed as the bearing characteristics number, and we'll see later why it is so. And r by c is the non-dimensional radius of the bearing, and L by c is the non-dimensional length of the bearing. Now, among these three non-dimensional parameters, the first parameter, eta n by p, is the important one. Now, here we try to understand the different lubrication mechanism. In 1902, Richard Stribeck studied the working of the hydrodynamic general bearings and found the existence of a minimum friction, as shown in the picture, depending on the operating conditions. This is probably the first time the lubrication regime understood. Richard Stribeck and Mayo Heresy are accredited as a pioneer researcher in this field. But much later, in 1932, McKee brothers experimented on general bearings and came up with a curve as shown below that shows the variation of coefficient of friction mu with the bearing characteristics number eta n by p. Now, since Richard Stribeck is probably the first researcher who understood the variation of friction with the working conditions of the working parameters of the bearing. The curve is known as Stribeck curve. Now, let us look at this curve carefully. It is a curve between coefficient of friction mu and eta n by p, which is a non-dimensional parameter. And as I said earlier, is often known as bearing characteristics number. Now, the horizontal axis could also be replaced as the ratio of the effective film thickness divided by the combined surface roughness. This is important because if the effective film thickness is larger than the combined surface roughness, then only there will be no contact. Otherwise, there will be contact. So if this ratio is low, we can expect contact or very close sliding when the surfaces are very close together. So then, if we now look at the bearing characteristic number, it is eta n by p. That means if either viscosity eta or surface speed n is small or load is large, then there will be a condition where the surfaces will be nearly in contact, and this condition is called BL or boundary lubrication. Now in the boundary lubrication, we'll discuss a bit more in detail later on. The film thickness is very small, maybe 1 or 2 molecular layer, and we can say that the film thickness is of the order of 0.005 micrometer, and the friction is also relatively high, 0.5 to 0.01. So this is the boundary lubrication where the surfaces are very close together, but probably not meeting each other. But the frictional characteristics are often guided by the solid friction laws. Then comes the mixed lubrication. In the mixed lubrication phase, there is some part of the contact is fairly close together. That means surfaces are close and may be touching almost, and some parts are lubricated, almost as hydrodynamic lubrication. So then this is why it is called mixed lubrication. It could be either boundary or hydrodynamic lubrication. And here the film thickness is of the order of 0.05 micron, and coefficient of friction is of the order of 0.05. Then comes another lubrication mode called elastohydrodynamic lubrication. As I say, we'll discuss this more in the detail, but here briefly, this is a lubrication mode which is caused due to the combined action of the displacement or deformation of the solids in contact or sliding surfaces and the hydrodynamic action. This is often described as a type of hydrodynamic lubrication, because here the film thickness is reasonably high and it is of the order of 0.025 micron and 0.05 to 2.5 micron, which is fairly high, relatively high compared to the other two lubrication modes. Then comes the hydrodynamic zone, which is on the rightmost side of the curve. This is the hydrodynamic zone. Here, the lubrication film thickness is fairly high and is of the order of 0.25 micron or more. And coefficient of friction is fairly low, of the order of 0.01. But there is one thing I want to remember here, that although we say that in the hydrodynamic zone, friction is low and surfaces are not supposed to touch each other, but there is one thing to be noted, that the friction slowly rises with the increase in the bearing characteristics number. This is not dry friction, or this is not solid friction. This friction is the churning friction or fluid friction, because there is a relatively thick layer of fluid between the two surfaces, and it is the churning of the fluid that causes friction, which adds to friction. So we have got 4 lubrication modes. Boundary lubrication, where surfaces are fairly close together and friction is fairly high. Then there is mixed lubrication, where some parts of the surfaces are behaves like boundary lubrication, and some parts behave like hydrodynamic lubrication, and this is why it is called mixed lubrication. Then there is elastohydrodynamic lubrication. In this mode, the lubrication is governed by the combined action of the deformation of the contacting surfaces and the hydrodynamic action of the fluid. Hydrodynamic lubrication, where the surfaces are fairly separated, and there should be ideally no contact. And here the film thickness is fairly high and friction is also fairly low. Then we go to a little more discussion at depth of boundary lubrication. Before we discuss boundary lubrication and other lubrication modes, I must make it clear that a lot of research has been carried out for last several decades and probably centuries to understand these lubrication modes. And obviously, a lot of information has been gathered and also a lot of research has been carried out. So in this small note, we probably cannot give a complete discussion of the lubrication modes, but we'll give a bird's eye view of the lubrication modes for an early understanding or easy understanding of lubrication modes. So in boundary lubrication, we expect surfaces to be fairly close together, and they are separated by one or two molecular layers, and the layers gets attached. Layer gets attached due to intermolecular forces, and the film strength are limited by the melting point of the lubricant, which is often in the order of 180 degrees or so. Now, we must consider this very carefully, because during the rubbing, heat is generated, and this increases the contact temperature. Exact contact temperature can be very high at the peaks of the asperities, but the average contact temperature or will be tolerable, not in the thousands of degrees centigrade. And if that temperature is in the order of 180 degrees centigrade, the layer, the boundary layer, will not be effective. The the attachment of the boundary layer decides or governs the no-slip condition in fluid mechanics, because this is due to the physical adsorption, and some molecules will be attached and some molecules may go out, but there will always be a layer as shown in the picture below. If we look at the variation of coefficient of friction against temperature, we'll see that temperature and friction will be fairly constant in the early earlier zone, because there the temperature does not rise fairly high to a fairly high level. But as the rubbing goes ahead or goes on, temperature will rise. And when the temperature increases beyond the transition temperature, in this case it will be 180 degrees or so, coefficient of friction will start rising as shown here. So this is a very brief description of physical adsorption, which is one type of boundary lubrication. Boundary lubrication can also be due to chemically adsorbed layer. These layers may be formed by adding vegetable or animal fats, which are polar active molecules, and they show great affinity for the metals at the active ends. In fact, in the book on history of tribology by Duncan Dawson, he has mentioned one very interesting point, that in the early days of Roman civilization, the chariots used to be nailed, the chariot wheels used to be nailed, and on the nails they used to put animal fats, which stops or help wear of the wheels. So animal fat is a good way of producing, producing a thin film of lubrication, which is ideally suited for boundary lubrication. So we can, if we have a fatty acid and with metal, then soaps will be formed. And these soaps are of low shear strength, and hence we get low friction. For example, if we look at stearic acid, which is C17, H35, COOH carboxylium plus Fe, then we get iron stearate. Now, this iron stearate can be represented as the carpet piles, which will be shown in the next page. And the height of the carpet pile will decide the friction, because longer the chain or longer the carpet pile, the lower will be the coefficient of friction. This is an example here. If you look at the picture, a metal surface on which a polar active fatty acid is adhering. So the end at the end of carbon atom to the metal surface will be addition, because they are different molecule or different atoms. But between hydrogen and hydrogen, there will be cohesion. Now this is a chemical bond, and as we apply shear force or shear stress, longer the chain, lower will be the friction, because we can imagine a larger, as I said earlier, carpet pile. Lower force will be required to bend it rather than a shorter chain. And this is what was proposed by W.B. Hardy, who proposed a relation of frictional coefficient of friction equal to B minus AM. B and A are the constants, and M is the molecular weight. So larger the molecular weight or larger the chain length, friction will be lower. So this is a very good way of understanding the chemically absorbed layer, and friction will obviously depend on the molecular weight, which decides the chain length. Now we come to films formed by chemical reactions. Just to remind you that all these films come under boundary lubrication. Now these films provide greater film strength compared to the other films that we described, and are used for most severe operating conditions, and they are usually known as EP additives. EP means extreme pressure additives. In fact, it is extreme temperature additive, because with a high pressure, high temperature is generated, and the films are required to last for higher temperature. The examples for these type of films are obtained by adding sulfur, chlorine, phosphorus, etc., which reacts at high temperature, 100 to 200 degrees centigrade, with the surfaces, and produces sulfides, chlorides, and phosphides. And these last till thousands of degrees centigrade. And these are known as EP additives, because they can take, they will lubricate the surface even up to a fairly high temperature. So we can conclude here that fatty acid can protect the surface for a lower temperature, say 100 to 200 degrees centigrade, and the coefficient of friction will be of the order of 0.07 to 0.15. But with the EP additives, sulfides, chlorides, phosphides, etc., and the films can retain up to thousands of degrees centigrade, and the temperature and the coefficient of friction will be on the order of 0.1 to 0.25. So this is an important point to remember, that fatty acid cannot give us protection from high temperature. For protection at high temperature, we need to use EP additives. Now, now there are preformed films. Now these are the protective coatings given to surfaces before the sliding or rubbing takes place. Because once the protective coating is present, the friction and wear expected to be low. Now, there are many different types of protective coating, but here we'll discuss only a few. Phosphating, firstly, then sulfidation, and then chromium plating, and then ion implantation. As I say, there are many other types of coating, but we'll restrict our discussion to only these four. Now, coming to the phosphating first, there are three main methods. Iron phosphating. This is used to provide steel surfaces with a good addition to painting. That means, again, it is a pre-treatment given to the steel surface for painting or oiling or any other operation that is needed. Zinc phosphating is again used for corrosion, protection against corrosion, and again it's a pre-treatment for steel and aluminum surfaces also prior to painting or oiling for cold flow pressing. So it's very clear that these are pre-treatment for further processing, painting or oiling. Finally, there is another type of phosphating called manganese phosphating, which resists adhesive wear of mechanical parts of internal combustion engines or bearing. It is a very well-known phosphating process, and typical thickness lies between 3 to 50 micron. This is not a very small or very thin layer, so it is supposed to give a good protection. The process forms a layer of insoluble phosphates on the material surface. Now, sulfidation. It is a process of installing sulfide ions in a material, and this is widely used for surface modification and corrosion protection. So again, this is a method of producing sulfides surface which gives protection and against corrosion and any other further processing. Then there is chromium plating. This is again a very well-known paint plating process, and this is electrochemical or electroplating process. A thin layer of chromium on a metal surface is produced by electroplating. This provides many other things, luster and hardening, and also collision protection. So chromium plating gives a decorative surface. It increases hardness and also gives corrosion protection. Then comes ion implantation. This is not often heard of, but this is a very important, useful process. Ion implantation is a process by which ions of specific elements, such as radium, are accelerated and directed at a solid target. The ions collide with the target's atoms, lose their energy, and come to rest at certain depth. Now, this is important. So this means that the effect of ion implantation will be felt only up to the depth where it comes to rest. Rest of the metal remains as it is. That means their properties are not changed. The ions change the electrical the elemental composition of the target material and causes physical, chemical, and electrical properties. The process is of much use and can be used in many different kinds of applications. But from the mechanical point of view, is an excellent way of hardening the surface without changing the bulk properties of the surface. So this is a hardening method. But here the problem, although it's a very robust method, but the process is costly. And this is why in many cases the process is not used or avoided. Now, apart from the pre-treatment, there is another type of lubricant called solid lubricants. We are often quite used to lubricate the surface by liquid lubricants, and we feel that that's the only way of lubricating the surface. But this is not so. There are a number of compounds such as molybdenum disulfide, PTFE, polytetrafluoroethylene, graphite, tungsten disulfide, nylon, polyethylene. These are all molybdenum. These are all solid lubricants, and they, when coated on the surface, will give a good protection of the surface because they produce a low shear strength film on the surface. And this low shear strength comes in most cases due to their layer lattice structure, at least molybdenum disulfide, graphite, tungsten disulfide comes to this group of material. This is a typical example of a layer lattice structure. The atoms in one layer, the distance between the atoms in one layer is much smaller than the distance between the two layers. Here, in the example, B is much more than A. And hence, when a shear force is applied, it bends easily and gives a low shear strength, and the friction comes down. So this is called layer lattice structure, and many of the solid lubricants work on this principle. Now, as I said, whatever we have discussed, boundary lubrication is just a bird's eye view, a very simplistic way of introducing boundary lubrication. There are much more have been researched, and many more information are available today. But we are giving a very simple introduction to the topic. Now we come to mixed lubrication. Here again, we will be restricting our discussion to a very introductory level. Mixed lubrication, as we said before, is a combination of lubrication in the boundary method and hydrodynamic member. Some part of the contact is in the boundary level, the boundary mode, and some portion is in the hydrodynamic mode. So there are basically two important lubrication methods between the boundary and the hydrodynamic lubrication. One is the mixed lubrication method, and other is the hydrodynamic lubrication mode. Both are very important, but we'll go through a very introductory discussion. As we said, mixed lubrication, the behavior is governed by the mixture of boundary and filtering effects. Some asperities may contact may some asperities may contact, and this may take place, and nano or multi-layer boundary film will be interacting, whilst a partial fluid film lubrication will be developed in the bulk of the material, bulk of the contact. The picture below shows some part is in the boundary form, like this one, and some part is in the hydrodynamic mode. So the analysis must be based on the boundary, the combination of boundary and hydrodynamic mode. A typical example of this type of lubrication mode is found in the impregnated bearing. Impregnated bearing are usually porous, made of porous material, which is material impregnated with lubricants, giving a lubricant reservoir. In this type of material, the pores are used as lubricant reservoir. Under load, the lubricant oozes out and lubricates the surface, and as the load is taken off, the lubricant goes back to the pore, and there is no lubricant, little lubricant left between the two surfaces. But in the other zone, in the zone shown here, we can expect hydrodynamic lubrication. So, as we said before, the porous metal is usually made by sintering a compressed metal powder, as an example, sintered iron or bronze, and the pores serve as lubricant reservoir. Again, as we discussed before, is a typical example of a sintered bearing or porous bearing. Here, the pores act as a reservoir of lubricants. They retain the lubricant until the load is applied onto them, and once the load comes, the lubricant oozes out, and then with the withdrawal of the load, the lubricant comes back. The load carrying and the frictional characteristics of these bearings depend on the properties of the metal matrix. As I say, it may either be iron or bronze or other type of metal matrix. Lubricant, what type of lubricant, whatever we are using, and the opposing surface, which is often steel. The use of these bearings are restricted to low sliding because it is expected to wear out, but it can take fairly reasonably high load. The behavior of these bearings may be analyzed in terms of hydrodynamic performance by assuming that a full fluid film exists in the clearance space. This is the clearance space, and the flow of lubricant within the porous material. The flow of lubricant within the porous material is governed by Darcy's law, given by Q flow rate is equal to minus K capital A divided by mu capital L delta P. Here K is the permeability, delta P is the pressure difference, L is the length of the material, and A is the cross-sectional area, and mu is the dynamic viscosity. So it is a simultaneous solution of Nernst equation and the flow equation for the porous matrix is required to find out the flow pattern, pressure distribution, and load carrying capacity. So more details are not given here. As I said, this is a very brief introduction to the services, but there is a vast knowledge available on this. One can go into the detail in many books available. Now we go to Elastohydrodynamic lubrication. As I said earlier, it's a lubrication mode where it's a combined action of the deformation of the contacting surfaces and the hydrodynamic action of the lubricant in between decides. This usually occurs where there is a very high contact pressure. For example, gear, cam, tappets, and very highly loaded other contacts. Here the surface elasticity is important, and hydrodynamic action obviously will be dictated by viscosity, load, speed, and other parameters. Here one very important point is that the viscosity is modified due to high pressure. Viscosity at any instant is equal to eta naught e to the power alpha p. Eta naught is the initial viscosity, and e to the power alpha p, alpha is the pressure viscosity coefficient. This is a typical property that can be obtained experimentally, and P is the pressure. So this is a very important point to remember, that the pressure is modified and that the viscosity is modified due to pressure, and it's given by eta equal to eta naught e to the power alpha p, alpha being the pressure viscosity coefficient. Now again, we, as I said, there's a vast information available on this. We'll give only a very short description of this. Let us look at the film shape and the pressure distribution. Film shape is fairly parallel most of the contact zone, but only at the end there is a dip that decides the minimum film thickness. And once the combined surface roughness is lower than that H minimum, I think the contact is safe. Now this dip is due to a bump in the pressure distribution. Pressure distribution is almost Hertzian most of the places, except at one end there is a spike. This is a typical characteristics of elastohydrodynamic lubrication, and possibly we can mention Professor Dawson and Higginson for discovering this novel method of lubrication. So we go to this minimum film thickness point again, because this minimum film thickness is an important issue here. Dawson and Higginson came up with an equation which is in terms of the elasticity and other parameters. H minimum is equal to 1.6 alpha to the power 0.6 e to the power 0.03, eta naught to the power 0.7, and u to the power 0.7, capital R to the power 0.43 divided by W to the power 0.13. Now let us look at it carefully. Alpha is the pressure viscosity coefficient, and obviously higher it is, higher the film thickness, because this gives higher viscosity. E is again this elasticity. Higher elasticity will produce higher deformation. Eta naught again is the initial viscosity that will be involved. Capital U is the combined relative velocity between the two surfaces given by U1 plus U2, which is again important point in finding the film thickness. This we'll see when we discuss hydrodynamic lubrication. And capital R is the equivalent radius that will also decide the film thickness. And the load is in the denominator. That's quite clear, because higher the load, lower would be the film thickness. So we can see that once the combined roughness between the two surfaces, sigma 1 plus sigma 2, sigma is the standard deviation of surface 1 and sigma 2 is the surface deviation, standard deviation of surface 2. The combination of this must be lower than the minimum film thickness to avoid contact. So this is a very important point to remember, and this we got from the research carried out by Dawson and Higginson much earlier, possibly in 1950s. So with this, we complete our lubrication regime discussion. As I said, much more can be learned and much more information is available, but this is just an introductory statement.